disappeared online. Is that the same problem?
I did have them down briefly, but they should be back up. When did you last check?
The page disappeared like all of last week, but now the page is back and all of my grades are 0.
If you go into an individual quiz item, does it still show? Okay. Because I can see that they're still there, so I can see them. I don't know why it's not showing for you.
As long as it's still there.
Yeah. At the end of the course, I'm going to go into each individual quiz and take the grades from there. So if anything's gone wrong there, send me an email and I'll look into it. Okay, cool. Kia ora koutou. Welcome back. So we're halfway through the week. So Lab 9 finished up yesterday and Lab 10 question set is now underway. So if you've already been to a computer lab session this afternoon, that's great. Otherwise, make sure you go to one tomorrow or Friday. They're a really valuable resource for you to use to work through those labs. And I think having a tutor there in person will make it a much more efficient process than working out all the problems by yourself. So that's how the course is really designed to work, is to give you lots of tutor support as you work through questions. Right, so we started talking yesterday about integration. So we talked about the indefinite integral, so finding the antiderivative. So we talked about coming up with some function, capital F, so that if I differentiate f, so if I take this output function, capital F plus c, and differentiate it, I'm going to end up with this function that I'm interested in, f of x. So this is the antiderivative, and it gives us a function as an output. So what we're going to talk about today is that second question that we looked at the start of yesterday's lecture, where we said, why do we do integration? And that second question is about, what if I've got a curve and I want to find the area under that curve? And so the definite integral helps us work towards that answer. So remember, the derivative tells us the slope of a curve. The integral tells us the area under a curve. So all of calculus, really, we can think of it algebraically in terms of functions, but we also want to be making connections to what that means in terms of the graph and what it looks like, that geometric interpretation. So you probably find one a bit more intuitive than the other. Some people really like working in algebra, some people really like working in pictures. But it's really important to make those connections across between the two, between the algebra and the geometric pictures. So we're going to introduce what's called the definite integral. And so the definite integral looks like this. So this might, what's happened there? Okay. So we've got a definite integral here, and the difference you'll notice is that now I've got a number a and b. So here, a, b is an interval. So a and b here are real numbers. And the definite integral gives us the output of a real number. So this gives us an output equals some real number. So we recall the indefinite integral, f of x dx, gives us outputs a function. So the examples we looked at yesterday, we output a function. Now we're adding this interval that we're looking at, and so the definite integral gives us a number. And so that's the key distinction between the two, between what they look like. So we make some assumptions in Math 101 that we're looking at continuous functions on a closed finite interval. So AB is some closed finite interval. If you go on to further maths, you can, it can get a bit more complicated once you start introducing functions that are not continuous, or if you look at open intervals. So we can do things when we don't necessarily have these conditions, but it gets much more complex. And so in Math 101, we're going to make these assumptions, which makes the maths work out nicely. So some examples are if we have this definite integral from 0 to 2 of 3x squared, that gives us an output of 8. I'll talk in a couple of slides about how we get that answer, but these are just a couple of examples. So if I give you this definite integral from negative pi on 2 to pi on 2 of cosine, that gives us an output of 2. So quite different to the outputs we were seeing yesterday, where we were getting things like sine of x or cubic functions. In this instance, when we're looking at definite integrals, we're expecting a number as an output. So what does this tell us? What does this number represent? So graphically, this number tells us something about the area between that curve and the x-axis. I've picked this curve here, so say this is my f of x curve. It starts positive, so we're interested in this interval. Okay, just bear with me a second. I'm going to see if there's a function I can turn off. Okay, hopefully that stabilizes. Right. So we are looking at our function f of x over this interval a to b. So we're interested in this closed interval from a to b. And my function starts positive, it dips below, it goes back up. Just pick some random function. It doesn't matter what the particular function is, but this is its graph. And so the definite integral of this function from a to b tells us this area, A1, minus this area, A2, and then plus the area, A3. So it gives us some measure of the area between the curve and the x-axis, except that anything that's below the x-axis counts as negative area. So this area counts as negative, and then areas above the x-axis are counted as positive. And so we can use this definite integral gives us a number that represents how much area is above the x-axis relative to the area below the x-axis. So we call this the signed area of the graph between the graph and the x-axis. So that signed area means add what's above the x-axis, subtract what's below the x-axis, and that gives us our total signed area over that interval. So we'll talk, I think tomorrow, we look at geometric area. So signed area, we add whatever's above the x-axis, so in this case A1 plus A3, and we subtract what's below. Tomorrow we'll talk about geometric area. And so geometric area, we're interested in what's the actual true area of this shape. And so for geometric area, we would want to add A1 plus A2 plus A3. So you could imagine geometric area answers the question about if I was to paint this surface that I've got shaded in grey, how much paint would I need? I would need to know the actual true geometric area of this shape. The signed area answers the question about how much is above the x-axis relative to how much is below. So this is what the definite integral tells us, geometrically. It tells us this area. So here's a little summary slide that just reiterates the things I've been talking about. So if it's above the x-axis, it becomes positive. If it's below, it's negative. So on your notes, have a look at, this is a graph of x times sine of x. On that little graph, add in pluses and minuses for which parts you would need to add or subtract from your definite integral. So hopefully you've put pluses on the outside 2 bits and a minus in the middle, because we've got our x-axis cutting through there. Okay, so I put a little reminder for us here. Before we get to how do we use integration, the indefinite integral that we've been working on to solve these problems, let's just stop and think about area. So I've got a shape, a graph, a function here, x minus 4. So it's linear, so I can easily sketch that. And so it's going to look like this. So I'm interested in the interval from 0 to 4, and I want the area between my function and the x-axis, so I want this yellow shaded area. So let's think about, let's call that, we can just call it A, and think about what is the area A. Well, A is just a triangle, so half times base times height. We don't need calculus to find this area. We can just calculate half times base times height, so that is half times base of 4 and height of 4. 4 times 2 is 8. So the area of that triangle is 8. So what is the value of my definite integral going to be? What do we think? Minus 8, yeah, why? Yeah, because it's below the x-axis, it's negative. Great. So if we've got straight lines, we can calculate the definite integral. Wouldn't that be great if all of our functions we were looking at were straight lines? Another quick example, still using our straight line so that we don't need to use integration to calculate it. So now I've got negative 4, has an intercept at 4, and it keeps, we're interested in the interval up to 5, and that's going to be, so f of 5 is going to be 1. So this is my straight line. Okay. So now we want to find this definite integral. So what are we going to need to do? Well, we want to find the area, we want to find the signed area. So our little graph from before looked like this, where we calculate area above, and that's positive, and area below, and that's negative. So I might put a little reminders for myself I want to find that area, and that's negative. I want to find that area, and that's positive. So let's call this A1 and A2. So our definite integral, our signed area, is going to be subtract A1 and then add A2. So we know A1 equals 8 from the previous slide. A2 again is just another triangle. So we want half times base times height, which is half times, got a base from 4 to 5, so that's base of 1. And height goes from y equals 0 to y equals 1, so again the height is 1. So A2 is area a half, and so our definite integral is subtract A1, so minus 8, plus A2, so plus a half. So that's negative 7.5, or if we want that just as a single fraction, negative 15 over 2. So if we've got straight lines, we can work out these signed areas. But the clue that we're using this integration symbol within our definite integral tells us that we should be able to use the antiderivative that we've been working on already to help us solve these problems, which we're going to need if we get lines that are more complex than just straight lines. So if we want the area under a curve that's not just a straight line, we need to use the antiderivative. So we could run through our example from the previous slides and check that we get the same answer. So find the antiderivative of f. So the antiderivative of x minus 4 is x squared on 2, take 4x, plus c. And then our next step says evaluate this at each of the end points of our interval. So our interval is from 0 to 4, if we're looking at our first example. So we want to calculate this antiderivative at 0. So let's call that capital F. Evaluated at 0, that's a half times 0, take 0 plus c. And then evaluated at 4, it's a half times 4 squared, take 4 times 4 plus c. And so that's 8 take 16 is negative 8. And then our next step says subtract the value at the left-hand endpoint. So the left-hand endpoint is 0 from the value at the right-hand endpoint, so 4. So we take capital F of 4 minus capital F of 0, which is negative 8 minus 0, which is negative 8, which is what we got in the previous example. So same answer we got in our first example above. One thing that I do want to point out is that actually in these definite integrals we can just ignore that plus c. Because when we do this subtraction step, I've said f of 4 minus f of 0 is negative 8 minus 0. Really, if we wanted to put in the plus c's, which I've dropped from here, that will be negative 8 plus c minus 0 plus c, or minus c, is just going to be negative 8. So the c's kind of cancel out. So when we're using definite integrals, we don't have to worry about our constant c because it cancels out when we do this subtraction. So what this example illustrates, we're not going to prove it, but it's a nice illustration for what's called the fundamental theorem of calculus. And this fundamental theorem ties together the antiderivative and the definite integral. This theorem says why integration answers both of the questions of how do we undo differentiation and how do we find the area under a curve. The fundamental theorem of calculus is what says these are both answered by integration. So this theorem sums up how we can find the definite integral. So this tells us how to find definite integral. It says find the antiderivative and take f of b minus f of a. So evaluate that antiderivative at each end of the interval and voila, you've found the definite integral, which tells you the signed area under the curve. F of x or f of t. Okay. So one thing to point out is some notation that I'll use. So I've got a note here. If I say capital F of x and then use this square bracket on the right with a on the bottom and b on the superscript at the top, what that means is evaluate f at the top number, b, and then subtract evaluating f at the bottom number. So this is just a shorthand, shorthand notation, which is useful when you're writing out your working out. Okay. So I'll work through some examples at this point, linking back again to our straight line example and then working on to some other functions. But are there any questions at this point before we move on?
Is there a name for the squiggle?
Yep. So the integration symbol.
Is there a name for it? Or is
I'm sure there is a name for it. I can't think of it off the top of my head. I would call this whole thing an integral. I would call this guy the integrand.
Are you making this up?
No. Just trying to think. No one's ever asked me that before. I'll find out for you. Cool. So we've got some notation. We know now how to work out these definite integrals, these signed areas. And so let's work through some examples so we can put those in practice. Okay, so this first example, we've got the same straight line example that we saw before. So we're hoping that we can apply this method of the fundamental theorem of calculus and end up with the same answer we did before. So we're hoping that this gives us negative 15 on 2. And so let's check. So our process, just like we worked through step by step before, the first thing to do is to find the antiderivative of our function. So the antiderivative of x minus 4 is a half x squared take 4x. And then we remind ourselves we want to evaluate this over the interval from 0 to 5. Then we do that evaluation. So I would recommend when you're writing out the working, I like to give myself 2 sets of brackets with a minus sign in between to then fill in. Partly because it's really easy to forget those brackets and then you're not subtracting the whole right-hand bracket. It just makes the working out a bit nicer. And then inside this first bracket, we're going to evaluate this function at 5. Inside the second bracket, we're going to evaluate the function at 0. And so let's evaluate this at 5. So we get a half times 5 squared, which is 25. Take 4 times 5, which is 20. And then if I evaluate this function again at 0, I get 0 take 0. So in this example, I'm just subtracting 0, so that's nice, I get to ignore that. So this is 25 on 2, subtract 20. And so if I want to work that out without a calculator, I might write that as subtract 40 on 2. And that becomes negative 15 on 2, which is exactly what we were expecting from our triangle calculations. All right. Let's work through this next example. So now we're looking, I'll draw a quick sketch, may as well. So now we've got this quadratic, t squared, and we're interested in t from 1 to 3. So now we want to find this area under the quadratic, and so we can see that that's going to be really difficult to do accurately without using integration, without this fundamental theorem of calculus. So let's follow our fundamental theorem of calculus process. So first we find the antiderivative. So t squared becomes t cubed on 3. And then we remind ourselves we want to evaluate from 1 to 3. I'm going to give myself my nice brackets to fill in. Evaluate first at t equals 3, and second at the bottom number, t equals 1. So this becomes a third times 3 to the power of 3. Take a third times 1 to the power of 3. So 3 cubed divided by 3 is 9. Subtract a third, which I can leave it like that, or I can simplify to 26 on 3. So when you're writing this out, I've written those green notes telling you what we're evaluating at. I don't necessarily expect that you'll write those in your working, but I do strongly recommend that you'll need these brackets. Especially once the terms start to get a bit more complicated and you get something that's got multiple terms in it. So we've seen a couple of examples of this fundamental theorem of calculus. And so we can see that this area under this curve here is going to be 26 on 3. That area under the quadratic. Does anyone have any questions about the process at this point before I go on to some even more examples? Yeah?
What happened to C?
What happened to C? Yeah, it cancels out. So let's think about that a bit more. So the question was, what happened to C? Suppose in this first example, I do my antiderivative. And so if I was doing the antiderivative, I would want that plus C there. And then I evaluate this function at x equals 5 and x equals 0. So I've got 25 on 2, take 20 plus C. And then subtracting 0, take 0 plus C. Well, I'm doing C minus C. So that becomes plus C minus C, so they cancel out. So that's the algebraic answer as to why that happens. Any other questions? That was a good one. Yes?
Do the two C's have to be equal to each other? Like if they're both constants, is maybe any value?
So C if I'm just finding the general antiderivative, say I want x minus 4 dx. Right, so if I want the indefinite integral, that becomes a half x squared minus 4x plus c. C there is a constant term. I'm not allowed to just pick a number and put it in. It's just plus c, plus a constant. If I know extra information about this particular curve, then yes, we would put in a particular number. So if I have an actual curve, say I know that f of x is a half x squared, take 4x plus 5. If I have a particular value, then it's going to be plus 5 and minus 5 again, and they're going to cancel out. And so that then links back to our geometric interpretation of what's going on. That if we've got this, remember this definite integral represents the signed area. And so if I so this function here, this small f, remember our function represents the slope of our antiderivative. And so the slope doesn't change if we change that constant term. Remember we had our solution curves, we saw an example where we had a few different solution curves that were shifted up and down. The slope doesn't change. And so that kind of links in with the geometric interpretation of what's going on. Yeah, good question. Anything else? Or we'll move on to more examples. Okay. Right. One more example that's using essentially the power rule for integration. So here, my first step is find the antiderivative. But of course, if I want to find the antiderivative of the square root, it's actually nicer if I can write that in terms of powers of x. So let's write that as 4 times x to the power of a half. Remember, that's a neat trick I can often do, is to write things in terms of powers of x. Can we simplify? Can we write in terms of powers? Then I want to find the antiderivative. So remember, the power of x gets 1 added to it, so that becomes 3 on 2. And then we divide by that new power, or multiply by 2 on 3. So my function becomes 8 on 3 times x to the power of 3 on 2, and I want to evaluate from 1 to 9. I'm going to rewrite that as 8 on 3 x to the power of 3 on 2. Just so we can evaluate the next step a bit easier. Now I want to give myself my brackets to work with. And on the first term, I want to evaluate at x equals 9. And the second one, I want to evaluate at x equals 1. 8 on 3 times 9 to the power of 3 on 2. Subtract 8 on 3 times 1 to the power of 3 on 2, which is just 1. 9 to the power of 3 on 2, I should be able to start doing on my head at this stage, because I remember that this is 9 to the power of a half, and then cubed. 9 to the power of a half is just 3, so we've got 3 cubed. So we're taking 8 times 3 cubed divided by 3, which is just going to be 8 times 3 squared, or 8 times 9. And then I'm subtracting 8 on 3. So we get 72, take 8 on 3, and then maybe I want to write that as a single fraction, so I can write 72 as 216 on 3, take 8 on 3. Don't worry, I pre-calculated what that was. I can't instantaneously multiply in my head what is 72 times 3, which is 208 on 3. So that means we know the signed area under the curve of 4 times the square root of x. So if this is 4 times the square root of x, we can calculate the area under the curve from 1 to 9. As 208 on 3. So all of your working for the definite integrals should follow this template pretty much. Maybe you need to simplify your integral to start with so that you can integrate it, find the antiderivative easily. So let me write some steps. So maybe we need to simplify. Then we find the antiderivative. Maybe we can simplify again. Then we evaluate f of b, take f of a, and then we simplify. That's our steps for all of our definite integrals. Any questions about that process? I've got a couple more examples to work through where it starts to get a little bit trickier. Here we have what looks like this ugly fraction. But remember, if I've got a fraction or I've got one thing on the denominator, I can simplify that. I can split that up into 2 fractions. So this is e to the x on e. Nope, that's died. Hello? How's that? We're back? Yep. I can split this up. So this is e to the x on 2, subtract e to the negative x on 2 dx. And so, of course, I can evaluate each of those separately, or find the antiderivative separately. E to the x, the antiderivative is just e to the x on 2. And then e to the negative x, the antiderivative is going to be negative e to the negative x. And so we want to think about, that's jumping ahead a little bit in some ways to what's called integration by substitution. But if we think about if I wanted to differentiate e to the negative x, I would use, in some sense, the chain rule. So I want the derivative of the inside, which is going to be negative 1, times the derivative of the outside, which is e to the negative x. So my antiderivative gives me e to the negative x on 2. And then I want to evaluate all of this from 0 to 1. So this is an example where my nice big brackets come in handy because I've got 2 separate terms. So I would need to be careful with that subtraction. So we evaluate this first at 1. So this becomes e on 2 plus e to the negative 1 on 2. And my second term is e to the 0 is just 1. So this is 1 on 2 plus 1 on 2. And so now I can simplify a little bit. Well, I can't really simplify these first 2 terms. I could write this as e on 2 plus 1 on 2e. So remember that e to the negative 1 is 1 on e. And then subtract 1. And that's all I can really do to simplify this because I want the exact answer. So I don't want to put in E is 2.718, etc. I want to leave it like that. Okay. So the main things in there is to check what happens if you differentiate e to the negative x and check that we get negative e to the negative x. And the other trick that I'm pointing out here is that if we've got some fraction like this with two terms on the numerator and one term on the denominator, that's really just adding those two terms separately. That doesn't work if I've got something like a on b plus c. That's not equal to a on b plus a on c. You could put some real numbers in there and check that that doesn't work. What's happening here is really we recall fraction addition. That if I've got a common denominator, then I can just add the two top terms. That's all that's happening there. We see a similar thing in this next example. I'm looking at this and going, well, my first step, I want to find the antiderivative. How do I find the antiderivative of this rational function? We know how to use the quotient rule for differentiation. There is an equivalent in integration, but we don't cover it at all in Math 101. You'll get to that, I believe, next in eMath 118, Math 102. But we do know that if I've given you an integral that looks a bit tricky, maybe there's some simplification you can do first. And so we can simplify this to t squared on t plus 2t on t plus 4 on t. And then most of these terms simplify. So t squared on t is just t plus 2 plus 4 on t. And now I should be able to find the antiderivative of each of these terms separately. So we get a half t squared plus 2t plus 4 ln of the absolute value of t, evaluated from 1 to 2. And now I evaluate it at 2 and then subtract the evaluation at 1. So I won't work through that step by step, but this becomes 2 plus 4 plus 4 natural log of 2. Subtract a half plus 2 plus 4 natural log of 1. But we remember from way back in week 7, I think you did logs, ln of 1 is just 0. That's where our log function crosses the x-axis. So this simplifies to 7 over 2 plus 4 ln of 2. And that's our exact answer. That's all we can do to simplify that, because ln of 2 is not an exact number, not an exact, can't evaluate that exactly. So I've skipped some arithmetic working there. So that's something for you guys to check. Is that arithmetic and the simplification? So I do want to think about one more example before we finish up. Any questions about this example before I move on to the last one? So our process was exactly the same as previously. Simplify, which we did in the first 2 lines, find the antiderivative, evaluate at the endpoints of the interval, simplify again. Okay, so this next example, again, we're looking at velocity and displacement. So starting to tie back into some applications. So I've got some velocity function, v of t, which is 21 take 7 times the square root of t. So I've got a velocity of, I think it's a car coming to a stop over time. And so our first question is simply, how long does it take for the car to come to a complete stop? And so in these application questions, my first thing I want to do is think about what is that actually asking me in terms of the algebra and the maths that's going on. So this is asking me, when is the velocity equal to 0? Or we want to solve 0 equals this velocity function, 21 takes 7 square root of t. And so once I've defined for myself what is it that I actually want to find out, that's a fairly straightforward equation. I just need to rearrange. So this becomes 21 equals 7 square root of t. So square root of t equals 3, so t equals 9 seconds. So it takes 9 seconds for the car to come to a complete stop. And that corresponds with the graph that I've got here, that our velocity reaches 0, or the y-axis is 0, when time equals 9. Okay. So then our next question asks, what's the total distance that's travelled while the brakes are being applied? So that's going to be from when I start applying the brakes, from t equals 0, to when I come to a complete stop, t equals 9. So we're interested in the interval 0 to 9, and we're interested in the displacement, or the distance. And so we recall, how are velocity and displacement related? Well, velocity is the rate of change of displacement over time, ds dt. And so that means that the displacement, if I want the displacement, I need to integrate velocity. And so I want to find out how much displacement happens over those 9 seconds. So I want to find out from 0 to 9 what is the integral, definite integral of velocity. And so I want to calculate the definite integral from 0 to 9 of my function, 21 takes 7 square root of t, which, so I find the antiderivative, 21t, take 14, t to the power of 3 on 2 on 3, evaluated from 0 to 9. And if I leave you the working for you to fill in, that comes out to 63. So I'll leave that for you guys to fill in. 63, what? We're asking for distance, and we're interested in, the velocity is meters per second, so my distance is going to be meters. So the total distance travelled is 63 meters. Using that integration, the definite integral from 0 to 9 of my velocity function. And then my next question ties this back to the link between what's going on algebraically, so we can work through this algebraic method, and then we want to think about what's happening in the graph. So we've calculated this definite integral. That's what we calculated on the next slide. What does that represent on the graph? What does the definite integral tell us? Yep. Sorry? Yes, it tells us the total distance travelled. What does it tell us about the graph that we've got here? Yeah, it's the area. Tells me that that area is 63, represents 63 meters. So this tells us the area under V of t equals 21. Take 7 square root of t from, or over the interval 0 to 9. So remember, that's so a connection for you to keep making is that that definite integral tells you the signed area under the graph. And in this example, because all of the curve is above the x-axis, it tells us the geometric area as well. So tomorrow we're going to look at, if I've got the signed area, if I can calculate the signed area, but if I've got some function that dips above and below the x-axis, how can I use the fundamental theorem of calculus to find the actual geometric area? And so that's what we will work on tomorrow, but we'll finish up there for today. Thanks, folks. Hi, Jennifer. You will have received an email from the Central Exams Committee telling you what times. Yeah. So, sorry? So that will be in the email from the exams. It's organised by the Central Exams Committee, and they send out an email. I can't remember the date, but it'll be in your inbox already, so you can have a look at that. It's there. It should be there now. It should be. I think it was sent out a few weeks ago. So in your UC email address, you've got an email address at UC Live. Do you have an email address? Have you checked that? Yeah. So if you look at your official UC email address, that will tell you the details. It'll be something like it'll be 3 letters and a couple of numbers, something like that. You do need to access that email account. That's how we communicate with you. Just a second, I've just got to finish up here. No, it's all good. We'll get out of your way.